So let's get started. So today in 7.4, your book talks about population proportions and sample proportions. So, and really the central limit theorem as it relates to the proportion. You know, so it's very similar to what we did in 7.2 and 7.3. So we just have to find the standard deviation a little bit differently. So before we get working, we've got to define a few things. It says, this is on page 328. It says, in a population, the proportion who have a certain characteristic is called the population proportion. In a simple random sample of n individuals, let x be the number in the sample who have the characteristic. So the sample proportion would be p hat, and it would be, the ones that have the characteristic divided by the total. So x is the number that of individuals that have the characteristic, and n is the total population. Okay, or the sample, I should say, the random sample. So notation: the population proportion is denoted by p. Yeah, so p is the population proportion. And then, the sample proportion is p hat. So this guy right here is the sample proportion. So the sample proportion. So your book then goes over an example of a sample proportion. It says, to present an example, consider tossing a fair coin 5 times. This produces a sample of size n, right? Because you flip it 5 times, where each time in the each item in the sample is either a head or a tails. The proportion of times the coin lands heads will be the sample proportion, p hat. Because the coin is fair, because the probability that it lands on heads each time is 0.5, right? So you got a 50% chance it lands on heads. Therefore, the population proportion of heads. So let's go through this example. The population proportion of heads p is going to be 0.5 because it's a fair coin, right? A fair coin, if you flip it, you're going to get 0.5 each time. There are 32 possible samples, right? And the book goes over this. I'm not going to rewrite it. It's on the bottom of page 328.
328, yeah.
Yeah. In the table there, 7.2 lists them and presents the sample proportion p hat of heads for each one. And notice, so like if you had all tails, p hat would be 0 because so like I'm going to do just one of the examples. If you get all tails on your flip, you're just extremely unlucky if you're trying to get heads, right? Your p hat would be 0 divided by 5, right? So you just get 0. Where like if you get one head, let's say the last one winds up being head, p hat would be 1/5, which is 0.2. And then your book goes through all the possible scenarios that way, all the possible p hats. And so it says the column labeled p hat contains the values of the sample proportion for each of the 32 possible samples. Some of these values appear more than once, right? I mean, makes sense. You could get one head on the last one or one head on the fourth one, but it's going to have the same p hat, right? So like if you had tails, 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 heads, tails, this is going to have the same exact p hat of 0.2, right, as that previous one. Now, this keeps going forever this way. Or not forever, 32 times that way. Now, what's important, though, is how to find the mean and the standard deviation, because then we can use this later on with normal distributions. Well, it turns out the mean of this sample, or any sample, really, involving proportions, the mean of the sample proportions is always just the population proportion, okay? So for us, this is going to be 0.50 for this example, okay? The standard deviation looks a little different. We're going to have to know this for the test. The standard deviation of the sample proportions is the square root of the population proportion times 1 minus the population proportion, so it's complement, right? All over n. So I would just have this written down for the test. You'll have to know it when we get to the example for it. So for us, this example, if we want to do it by hand, which I think we have to do this part by hand. I don't know how to do that on the calculator. We'd have the square root of 0.5 times, 1 minus 0.5. All over. Now, n is going to be 5 because we flipped the coin 5 times. Okay? So each sample contains 5 flips. That's why the n is 5. So this would be the square root 0.5 times 0.5. I think that's 1.25. Let me make sure that's true. Oh, Lord, I thought too much on that one. Yeah, it's 0.25 divided by 5. So we wind up, now I'm going to just put all that in the calculator. So the square root of 0.25 divided by 5, make sure that's all under the radical, and you wind up with 0.2236.
Okay, is that 1 minus 5.5 n?
Nope.
Right there.
N is the
Down.
denominator, the 5.
Okay, what's that that's above it? In the 1 minus
0.5, 0.
Okay.
Yeah.
I thought so, but I couldn't quite read it.
Yeah, it's your sample proportion or your population proportion times its complement. Well, you know, with 0.5, the complement's 0.5. So it winds up being 0.5 times 0.5. Okay. So for this example, we had a mean of the sample proportions of 0.5 and the standard deviation of the sample proportions of 0.2236. Okay. And we can use that later on. I mean, when we get to some neat stuff later on, we're going to use this a lot like how we used the information in sections 1. Actually, sections really 2 and 3. Okay.
Mm-hmm.
Okay, so let's just move on to the next example. As the soft drink, this is example 7.22. The mean and standard deviation of the sampling distribution. So we got a soft drink. So the soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners. So notice this is a proportion of tickets that are winners, right? Is 0.25. So P equals 0.25. We know 1 out of every 4 cups we put a ticket on it. That's a winner. There's a total of 70 people. A total of 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let P hat be the proportion that win a prize. Find the mean and standard deviation. Well, the mean's easy because it's just going to be the population standard deviation or the population proportion. 0.25 because we know 1 out of every 4 should win. Will it win? We don't know. I mean, it's not going to be perfect, probably. And then the standard deviation, though, we got to do a little math for. So it would be the square root. And I'm going to do that same formula from before. So P hat 0.25 times 1 minus 0.25 all over 70. So we get the square root of 0.25 times 0.75 all over 70. And I'm just going to pop that in my calculator to make sure I get the same answer they do. So the square root 0.25 times 0.75 divided by 7. Yep. 0.0518. They rounded at the 4 decimal place spot. Okay. That was the example on page 7.22. Okay.
Okay, how did you get on the top there of the second square root 0.25 times 0.75?
1 minus 0.25.
Okay.
You see that, Lori?
Yeah. Got it. Okay, and the square root.
I'm going to write this down while you're going. Now we've got this, the central limit theorem, which we talked about before, but now we have the central limit theorem with proportions. Okay. So we can remember the central limit theorem said, hey, if you start sampling over and over and over again, your even if the sample doesn't come from a normal distribution, it will wind up being the good gosh, the proportion of the samples will be normally distributed. Well, the same thing happens with the central limit theorem. Now, there's a few rules that your book goes over for this to be true. It says, look, this is on the middle of page 330. It says, let p hat be the sample proportion for a sample size of n and the population proportion p. Look, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. Okay? If this is true, if these line up and are true, then the distribution of p hat is approximately normal with a mean and standard deviation. So if this is true, then we know that the distribution of p hat is the same as we said before. But what's nice is that it's normal. Okay? It's normal, and we can assume this, that the mean is just p. The mean of the sample proportions is p, and the standard deviation of the sample proportion is that formula again. So it's normal though. If this is true, then we've got a normal distribution of our sample proportion, which is kind of cool because then we can use that stuff in our calculator. We can use the normal CDF stuff in the calculator. Okay. So how do we use it? And let's see. Okay, I'm going to do this a little different than the book because our calculator can automatically jump to the conclusions. So I'm gonna do example 7.23, but I'm going to do it with a calculator because it makes our life a lot easier and not have to find the z-score and use charts and all that stuff. Okay, let's look at 7.23 now. It says, according to a Harris poll, chocolate is the favorite ice cream color for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 30? Now look, we have to check for normality on this proportion. And the way you do that, remember, is step 1, n times p has to be greater than or equal to 10, and n times p minus 1 has to be greater than or equal to 10. So for our example, n is 100, right? They sampled 100 Americans. And p is 0.27. Okay, p is 0.27. So let's check both of these. I'm going to take n 100 times 0.27. And I want to know, I'm going to put a question mark there. Is it greater than or equal to, not 100, but 10? That was smooth. I wrote 100, 10.0. Is it greater than 10? Well, yeah, 100 times 0.27 is 27. 27 is greater than 10. So it satisfies the first condition here. N times p is greater than or equal to 10. So now let's do n times p minus 1. Well, n times p minus 1, so n is still 100. So this would be, I got that backwards, didn't I? It's 1 minus p, guys. It's 1 minus p, not p minus 1. So 1 minus 0.27. I want to know, is that greater than 10? Yeah. 100 times 0.73. That's 73. Okay. So 1 minus 0.27, that's 0.73. And 100 times 0.73 is 73. So yeah, 73 is also greater than 10. So what this means is we can assume that this data comes from a normal distribution. Okay, we can assume this data is coming from a normal distribution. Therefore, we can answer a lot of cool stuff about it. Because it says, what is the probability that the sample proportion who prefer chocolate is greater than 0.3? So I'm going to say part 2, really. Probability of the sample proportion is greater than 0.3, right? now to get this, we need to know the mean, which we do. It's 0.27, right? Because it said 27% of Americans prefer chocolate, right? Now we have to find the standard deviation with that formula again. Now remember that formula was the square root of p, which we know is 0.27, times 1 minus p, 1 minus 0.27, all over 100. So we get the square root of 0.27 times 0.73 all over 100. Now I'm going to pop that in my calculator to wind up with this standard deviation. I get
That's-
0.0. I'm listening.
That's that 0.27 minus 0.73
It's times.
over 100.
Because it's
times.
times. Yeah.
Times
0.044396. And you really don't want to round it. You really don't want to round it if you're going to keep using it. You want a lot of decimal places, okay? I know you probably want to cut off score, but if it goes down this low, like get 5 or 6 decimal places, okay? So now the question though was, what's the probability the sample proportion is greater than 0.30? So look, we have a normal distribution. We can assume that because of the stuff up here, okay? We can assume a normal distribution because n times p is greater than 10 and n times 1 minus p is greater than 10. So we've got a nice normal distribution. We know it's centered at 0.27, right? 0.30 is over here somewhere. And we want to know what's the probability, really what we're asking, what's the probability that we sampled 100 people and it turns out more than 30% like chocolate, okay? They want that probability right there in that tail. And look, we've got the mean, we've got the standard deviation, we've got really our cutoff. The bottom cutoff is 0.3. This, we're just going to use the normal CDF again. Okay. The lower is going to be 0.3 because it wants to know what proportion are greater than 30%. The upper is going to be infinity. My mean and standard deviation are what I have to, what I found. So 0.27, and standard deviation is 0.0044396. That's not what they got. What did I do wrong?
0.249603.
Oh, you know what? I put in 0.0044. That's a much smaller standard deviation. Did you get 0.2496?
I got 0.2496. Yeah.
Yeah, that's what I got too. 0.2496. Now notice if you look at the book, because they use charts, they're going to get a different number. They got 0.2. If you look at on page 331, you'll see that they got 0.2483. And look, it's really close. And I'm going to tell you on the test, if you get something close to this answer, it's right. It'll be multiple choice, and the three or four solutions are going to be really far apart from each other for that reason, okay? Because there's rounding issues that happen with this aspect of the of statistics. It's just part of the issue with stats, okay? I mean, we could round it to 0.25 and it would solve it, right? It would solve that problem.
Okay, so the lower, upper,
okay.
Yeah, every time I go back to see what I have, it automatically clears everything out, and it's back to lower automatically has the negative infinity up there.
Really? Mine's usually just the last thing I did.
Okay, so the lower on that one would be 0.30.
Yep.
or 0.3. Upper would be the infinity.
Yep.
99. The mean is 0.27.
Mm-hmm.
And that other is 0.044396. Okay. And equals 2, seeing as I decided didn't want to do what I wanted it to do. 0.249. And you just wanted us to go like to 4 decimal points over?
Yeah, 4 decimal points is fine.
Okay.
I'll tell you when I make this test, I'm going to use the calculator to find the answers. So if you like doing the charts, then you're going to see the numbers are just going to be a little off, but it'll be really close to that answer.
Okay.
Okay, so let's do the next example. It talks about, hey, elections. Hey, perfect timing.
Oh, joy, oh, joy. I can't wait for it to be over.
Yeah, hey, tomorrow it's over. Woo-hoo. I know, I'm excited.
Tomorrow's going to be over, and then after that, it's going to be all the arguing.
Oh, yeah, we're not going to go to
Oh, you didn't count my vote. My vote wasn't counted here.
Okay, approximately 60% of eligible voters voted in 2016. So right away, I'm going to say that's going to be our P, right? 60% voted in 2016. If a sample of 88, so that's my N, eligible voters was polled, would it be unusual if less than half of them voted? Okay, so before we jump into this, let's make sure we can use the normal distribution, right? I've got to make sure N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10, okay? So N, for this example, is 88. P is 0.6. 88, I'm just going to do 88 times 0.6. It's going to be 52.8. Yeah, that's greater than 10, okay? Now, 88 times now 1 minus P, that's going to be 0.40, right? Because it's the conjugate, or not conjugate, but complement. Conjugate is an algebra term. So 88 times 0.4 is going to be 35.2. Yeah, we can use, so we can consider that this we can assume this population is from a normally distributed sample. Okay, it's the sample of the samples actually is normally distributed, which is kind of goofy, but that's what it is. Now, if we're going to do this though, we have to find the mean, which is super easy, of the samples. It's just P, right? And the standard deviation of the sample proportion, which we're going to do a little work for. So remember, this is going to be P times 1 minus P. Now I'm going to skip a step. 1 minus P is just 0.40, right? All over our sample, which is 88. And I'm just going to crack that in the calculator. So square root 0.6 times 0.4 divided by 88. I guess mine automatically puts it underneath there. 0.052223. Why not? The 3 2s, yeah. We'll use that many. Okay. 0.052223. So I've got my mean. I've got my standard deviation. And I really now need to see, what is it asking me? Is it unusual if less than half voted? So let's see. If I want to do my distribution, my midpoint here, my mean, is going to be 0.6, right? And I want to know what's the area to the left of that. Wait. Hold on. If less than half. Oh, no, this isn't right. Okay. It's not 0.6 because I want to know, is it unusual if less than half? That's 0.5, right? Whoop. I'm going to mark that out. My brain.
It's Monday.
It is Monday. We'll blame it on that today. If 0.6 is here, 0.5 would be over here somewhere, right? I want to know the area here, right? Do 0.4, does 0.2 vote, right? Area to the left. So I'm going to use my calculator again, right? So again, now if I use my calculator, negative infinity to the left, and then to the right, it's going to be 0.5. And then I've got my standard deviation and my mean here. So I go to second, second R, normal CDF. My lower here is going to be negative 1 E99, right? Because it goes forever to the left. It's going to stop at 0.5. My mean we know is 60 because it says 60% of voters come out to vote. And my standard deviation is 0.052223. And it tells us that 0.02775. So we've got a probability of 0.02775 that less than half come out. So probability of 0.02775 that less than half show up. In, was it 2016, I think, is the example. Okay. Now remember, this was a question on the test. If we get a probability of 0.02775, would that be considered unusual? Do you remember this, Lori?
Yeah.
Why is it unusual?
Because it's a weird ass number.
Not that it's a weird number. It's because it's less than 0.05. Less than 0.05. Ooh. Less than 0.05. So because it was less than 0.05, we considered, or your book considers that unusual. I'll tell you, that's not necessarily a problem. Stick to your book for that topic, okay?
Okay. I'm trying to write this all down as we go.
You're fine. I'll slow down right here for a second.
I know you're used to going quick.
Yeah, and it is hard. I'll say that's been a challenge with the Zoom sessions whenever there's not people in the classroom, because a lot of my speed is dictated on students, you know.
Mm-hmm. I'm your faithful, loyal student.
You are. I mean, you've shown up. If anything, right? You've shown up. So for homework, in this is one of those short sections, like I told you. Like, look, if you look back, this section only goes from 328 to 331. It's a 3-page section.
Right.
But it starts on 329, and I want you to do 1 through. Shouldn't be that many. Yeah, 1 through 27 odd. It's only about 13 questions. This is it starts on page 329 for section 7.5. Nope, 7.4. We're skipping 7.5. 1 through 27 odd. Okay, so now this leads us into 7.6. I'm skipping 7.5, guys. If you want to read 7.5, you're more than welcome to. But 7.6 actually is really more important for what we're going to be doing later. So we need to talk about it. So it's assessing normality. And look, to do some of the really neat stuff we're going to do over the next few chapters, really like 2 chapters, we have to make sure our data comes from a normal distribution, okay? That our data is normally distributed. And there's a few ways to assess that normality just to make sure that it is actually normally distributed data. And your book does a really good summary on the bottom of page 341. And it says, look, we have to reject the assumption that a population is approximately normal if a sample has any of the following. So if the sample has outliers, it's got to go away. If it's skewed, it's got to go away. Or if it's multimodal. So what that means, it has more than one distinct mode. So I'm going to kind of show you what that looks like visually first. And actually, 1 and 2 can kind of go together. Okay, 1 and 2 I can kind of draw something where they go together. Let's say we've got this distribution, and let's say, it was a test, and a lot of people did really bad. Okay, so it was very common to have the proportion or the I'm sorry, the average was really kind of centered around 60, but a few people kept making higher grades. And so what happens is you have this skewness. Now remember, I know we talked about this in the past, but this is called right skew. Okay, this is the number 2 part. So it says 2, the sample exhibits a large degree of skewness. This is right skew. Left skew would be the opposite. So like, let's say a lot of people made 60s, but then a few out here made really bad, really low grades. Okay, this would be left skew. So really, you can't have this. Now, that's the skew issue, is whenever, a lot of the population is kind of centered around one spot, and then you've got you got stragglers, okay? And then the sample contains an outlier. We defined outliers. Remember with box plots, we defined outliers and how to find an outlier. And that your book actually starts there, talking about box plots. And remember, if it was so far away, and we determined that by 1.5 interquartile ranges from either the 25th percentile or the 75th percentile. I'm not worried about this, guys. I'm not going to put the algebra on the test. Okay, it's more about the definitions. And then it talks about the bimodal. A bimodal graph, I'll tell you, I'll see bimodal tests whenever I have students that maybe show up or don't show up. Okay, so let's say I gave a test and half of the class had shown up and done the work and the other class had not. What I'll see is, let's say that for the group that showed up, it would be pretty normal to see them maybe make around an 80. But then the group that didn't, now there might be some people that score high, but you'll see it'll kind of pop back up at some low grade. This would be bimodal, where the groups are for some reason separated. Look, I'll tell you, we would have bimodal data if we looked at heights and we lumped everybody together. If we looked at heights and we didn't separate males and females, remember, I think it was 57 and 59 were the averages for male, female. We would see this. It would look kind of like this. I mean, there's a lot of overlap, so it would kind of look like that. This would be bimodal as well, where you got the average height of the males, and now there's a lot of males and females in between, right? But it doesn't go up there. It's just going to go down. We're going to have more females around the 57. So it would look like this. So bimodal just means there's more than one mode. We're not going to have one single nice normal distribution. Remember, guys, the goal is to have this going on, right? The goal is to have this, where we have the mean and the mode and the median all lining up in this perfect distribution. And if we have skewness, we don't have this. If we have bimodal, we don't have this. If we have outliers, we don't have this either, okay, right? If we have outliers, we actually kind of have a form of skewness. And it throws off the mean and the median. That's all I wanted to go over.